Welcome. In this session, we'll explore some extra material. What we'll do is we'll explore the Lagrange function for a constrained optimization problem in a little more detail. So let's look at this problem, which is quite typical. What we have here is a quadratic objective function, so that contains a quadratic form and a linear term. The property function is a linear equality. We're going to assume that the matrix in the objective is symmetric, positive, definite, and we'll assume that the constraints are full rank, which means that there's no redundancy in them and that there's at least one degree of freedom. To do some derivations, we'll recall the definition of the Hessian, and we'll also recall a property of dot products for linear algebra. So let's consider the Hessian matrix of the Lagrange function. And we begin by writing that Lagrange function, and that has a vector argument and the Lagrange multipliers, and that is defined as the objective plus the dot product between the multipliers and the property function. And when we expand that in our case, that is 1/2 of W transpose K W plus a possible linear constraint on linear component to the objective plus our multipliers, and the property is a constraint matrix times the argument minus a constraint vector. And we begin by differentiating this. So the gradient of the Lagrange is, so this is going to be a long one form, and the first part of this one form will be the derivative of the Lagrange function with respect to W, and then the second part will be the derivative with respect to the multipliers. If I differentiate this with respect to the argument, that works out to be W transpose K plus the linear term in the objective plus, and I can expand that is U transpose MW minus mu transpose C, and the derivative with respect to W will then be mu transpose times M. And let's put a comma so that we indicate where we're stopping all of this. So that will be one part, and then when I differentiate this with respect to mu, this all goes away, and then this will be W transpose M transpose mu, so that will be W transpose M transpose. And the next thing that we do is we have to transpose that one form into a vector so that we can then take its gradient. So the gradient of the Lagrange function transposed is a vector, and this term is, that would be K transpose W, but because K is symmetric, I can write that as K times W plus Q plus the transpose of this is M transpose mu, and this term when transposed is M times W transpose. And now I have the transpose of the gradient of the Lagrange function. The next thing I do is I want to now take the gradient of that. So when I do this, I'll treat this row as a function and this row as a function and differentiate them separately. And so the first entry of the Hessian of the Lagrange function is the derivative of this term with respect to W is K and 0, so that is simply K. The next entry in the Hessian matrix is, this will be this function differentiated with respect to mu, and so that will be M transpose. I then take this with respect to W. Oh, that shouldn't be a transpose, that should just be a W. With respect to W, and that is an M, and then take this and differentiate it with respect to mu, and that is 0. And so we have a remarkable result, which is that the Hessian matrix of the Lagrange function is the matrix that we were using to get the primal formulation. Further in the notes, I won't go through these derivations because they're slightly long, tedious linear algebra, but in the notes I show you how to find two kinds of vectors. I'll show you a vector that has a positive, a strictly positive quadratic form with this Hessian, and another that has a strictly negative form with that Hessian. And what that means is that this Hessian matrix is indefinite. So we can conclude that the Hessian matrix of the Lagrange is a saddle point. And that is an important result for us because we know to be cautious whenever we have a stationary point that's a saddle point. And this observation is one of the many things that are underlying a reluctance to use this matrix, because we can get instabilities or numerical inaccuracies when we're dealing with an indefinite matrix and we're trying to solve a problem at its saddle point.